Hello, friends. I am Satish Lele. I am a chemical engineer. I am working in field of piping for last 30 years. This video is part of my chemical process piping channel on YouTube. This video is about protection of pipelines from corrosion. Corrosion is the gradual destruction of material, usually metals, by chemical reaction with its environment. In the most common use of the word, this means the electrochemical oxidation of metals in reaction with an oxidant such as oxygen. Rusting, the formation of iron oxides, is a well-known example of electrochemical corrosion. This type of damage typically produces oxide S or salt S of the original metal. Corrosion can also occur in materials other than metals, such as ceramics or polymers, although in this context, the term degradation is more common. Corrosion degrades the useful properties of materials and structures, including strength, appearance and permeability to liquids and gases. Many structural alloys corrode merely from exposure to moisture in air, but the process can be strongly affected by exposure to certain substances. Corrosion can be concentrated locally to form a pit or crack, or it can extend across a wide area more or less uniformly corroding the surface. Because corrosion is a diffusion-controlled process, it occurs on exposed surfaces. As a result, methods to reduce the activity of the exposed surface, such as passivation and chromate conversion, can increase a material's corrosion resistance. However, some corrosion mechanisms are less visible and less predictable. Galvanic corrosion. Galvanic corrosion occurs when two different metals have physical or electrical contact with each other and are immersed in a common electrolyte, or when the same metal is exposed to electrolyte with different concentrations. In a galvanic couple, the more active metal, the anode, corrodes at an accelerated rate, and the more noble metal, the cathode, corrodes at a retarded rate. When immersed separately, each metal corrodes at its own rate. What type of metal to use is readily determined by following the galvanic series. Metals must be far apart on galvanic series. Metals must be in electrical contact. Metal-to-metal junction must be bridged by electrolyte. Zinc is often used as a sacrificial anode for steel structures. Galvanic corrosion is of major interest to the marine industry and also anywhere water, containing salts, contacts pipes or metal structures. Factors such as relative size of anode, types of metal, and operating conditions such as temperature, humidity, salinity, etc., affect galvanic corrosion. The surface area ratio of the anode and cathode directly affects the corrosion rates of the materials. Galvanic corrosion is often utilized in sacrificial anodes. Galvanic series. In a given environment, one metal will be either more noble or more active than others, based on how strongly its ions are bound to the surface. Two metals in electrical contact share the same electrons, so that the tug of war at each surface is analogous to competition for free electrons between the two materials. Using the electrolyte as a host for the flow of ions in the same direction, the active metal will take electrons from the noble one. The resulting mass flow or electrical current can be measured to establish a hierarchy of materials in the medium of immersed. This hierarchy is called a galvanic series and is useful in predicting and understanding corrosion. Corrosion removal. Often it is possible to chemically remove the products of corrosion. For example, phosphoric acid in the form of jelly is often applied to ferrous tools or surfaces to remove rust. Corrosion removal should not be confused with electropolishing, which removes some layers of the underlying metal to make a smooth surface. Phosphoric acid may also be used to electropolish copper, but it does this by removing copper, not the products of copper corrosion. Some metals are more intrinsically resistant to corrosion than others. There are various ways of protecting metals from corrosion, including painting, hot dip galvanizing, and combinations of these. Passivation. Passivation refers to the spontaneous formation of an ultra-thin film of corrosion products known as passive film on the metal's surface that act as a barrier to further oxidation. The chemical composition and microstructure of a passive film are different from the underlying metal. Typical passive film thickness on aluminum, stainless steels and alloys is within 10 nanometers. The passive film is different from oxide layers that are formed upon heating and are in the micrometer thickness range. The passive film recovers if removed or damaged, whereas the outside layer does not. Passivation in natural environments such as air, water and soil at moderate pH is seen in such materials as aluminum, stainless steel, titanium, and silicon. Passivation is primarily determined by metallurgical and environmental factors. The effect of pH is summarized using Porbike's diagrams, but many other factors are influential. Some conditions that inhibit passivation include high pH for aluminum and zinc, low pH or the presence of chloride ions for stainless steel, high temperature for titanium, in which case the oxide dissolves into the metal, rather than the electrolyte and fluoride ions for silicon. Passivation is extremely useful in mitigating corrosion damage. However, even a high-quality alloy will corrode if its ability to form a passivating film is hindered. Proper selection of the right grade of material for the specific environment is important for the long-lasting performance of this group of materials. If breakdown occurs in the passive film due to chemical or mechanical factors, the resulting major modes of corrosion may include pitting corrosion, crevice corrosion, and stress corrosion cracking. Pitting corrosion. Certain conditions, such as low concentrations of oxygen or high concentrations of species such as chloride which compete as anions, can interfere with a given alloy's ability to reform a passivating film. In the worst case, almost all of the surface will remain protected, but tiny local fluctuations will degrade the oxide film in a few critical points. Corrosion at these points will be greatly amplified and can cause corrosion pits of several types, depending upon conditions. While the corrosion pits only nucleate under fairly extreme circumstances, they can continue to grow even when conditions return to normal. Since the interior of a pit is naturally deprived of oxygen and locally the pH decreases to very low values and the corrosion rate increases due to an autocatalytic process. In extreme cases, the sharp tips of extremely long and narrow corrosion pits can cause stress concentration to the point that otherwise tough alloys can shatter. A thin film pierced by an invisibly small hole can hide a thumb-sized pit from view. These problems are especially dangerous because they are difficult to detect before a part or structure fails. Pitting remains among the most common and damaging forms of corrosion in passivated alloys, but it can be prevented by control of the alloy's environment. Stainless steel can pose special corrosion challenges. since its passivating behavior relies on the presence of a major alloying component of at least 11.5% chromium. Because of the elevated temperatures of welding and heat treatment, chromium carbides can form in the grain boundaries of stainless alloys. This chemical reaction robs the material of chromium in zones near the grain boundary, making those areas much less resistant to corrosion. This creates a galvanic coupled with the well-protected alloy nearby, which leads to weld decay corrosion of the grain boundaries in the heat-affected zones of highly corrosive environments. The stainless steel is said to be sensitized as chromium carbides are formed in the microstructure. A typical microstructure of a normalized Type 300 for stainless steel shows no signs of sensitization, while a heavily sensitized steel shows the presence of grain boundary precipitates. The dark lines in the sensitized microstructure are networks of chromium carbides formed along the grain boundaries. Dark lines in the sensitized microstructure are networks of chromium carbides formed along grain boundaries. Corrosion is limited to very narrow zones adjacent to weld, often only a few micrometers across, making it even less noticeable. Crevice corrosion. Crevice corrosion is a localized form of corrosion occurring in confined spaces or crevices, to which the access of the working fluid from the environment is limited. Formation of a differential aeration cell leads to corrosion inside the crevices. Examples of crevices are gaps and contact areas between parts, under gaskets or seals, inside cracks and seams, spaces filled with deposits and under sludge piles. Crevice corrosion is influenced by the crevice type, metal, non-metal crevice geometry, size, surface finish, and metallurgical and environmental factors. Microbial corrosion. Microbial corrosion, or commonly known as microbiologically influenced corrosion or mic, is a corrosion caused or promoted by microorganisms, usually chemodatatrophs. It can apply to both metallic and non-metallic materials, in the presence or absence of oxygen. Sulfate-reducing bacteria are active in the absence of oxygen and anaerobically produce hydrogen sulfide, causing sulfide stress cracking. In the presence of oxygen, aerobic some bacteria may directly oxidize iron to iron oxides and hydroxides. Other bacteria oxidize sulfur and produce sulfuric acid, causing biogenic sulfide corrosion. Concentration cells can form in the deposits of corrosion products, leading to localized corrosion. High-temperature corrosion. High-temperature corrosion is chemical deterioration of a material, typically on metal, as a result of heating. This non-galvanic form of corrosion can occur when a metal is subjected to a hot atmosphere containing oxygen, sulfur, or other compounds capable of oxidizing or assisting the oxidation of the material concerned. Products of high-temperature corrosion can potentially be turned to advantage of the engineer. Formation of oxides on stainless steels can provide protective layer preventing further atmospheric attack, allowing for material to be used for sustained periods at both room and high temperatures in hostile conditions. Such high-temperature corrosion products, in the form of compact epoxide layer glazes, prevent or reduce or during high-temperature sliding contact of metallic or metallic and ceramic surfaces. Metal dusting. Metal dusting is a catastrophic form of corrosion that occurs when susceptible materials are exposed to environments with high carbon activities, such as synthesis gas and other high co-environments. The corrosion manifests itself as a breakup of bulk metal to metal powder. The suspected mechanism is firstly the deposition of a graphite layer on the surface of the metal. usually from carbon monoxide or CO in the vapor phase. This graphite layer is then thought to form metastable M3C species, where M is the metal which migrate away from the metal surface. However, in some machines no M3C species is observed, indicating the direct transfer of metal atoms into the graphite layer.